So welcome to the second lecture of week 10, and last time we learnt about the intermediate value theorem, which says that if you have a continuous function which is real valued and lives on a compact interval ab, and y is any real number between the endpoint values fa and fb, then there exists a point c in the domain such that f of c is equal to y. In other words, this value y, which is between fa and fb, is attained. And today we will learn about the extreme value theorem, which is also about continuous functions on a compact interval. So here is the statement of the extreme value theorem. It says the following. So let a and b be two real numbers where a is strictly less than b, and f is a real valued continuous function defined on this compact interval ab. Then the following hold. So there are several conclusions. The first is that the range or the image of f is a bounded subset of R. So we denote this range or the image of f by S, and that's the collection of all f of x's where x belongs to the domain of the function, which is this compact interval. Now, since this set is bounded and we also know it's non-empty, by the least upper bound property of R, we know that the supremum of S, the least upper bound, exists, and by the greatest lower bound property of R, we also know that the greatest lower bound of S, the infimum of S, also exists. And the real content of the extreme value theorem is that these values, they are attained. So there exist points C and D in the domain such that f of C is equal to this supremum and f of D is equal to this infimum. And then we note that since f of C itself belongs to the range, this f of C belongs to S. So the supremum of S belongs to S. So then we know that the supremum is really a maximum, and f of D also belongs to the range. So this infimum belongs to S, so that this infimum is actually a minimum. And here is a picture that we can keep in mind. So here is A, here is B, here is the compact interval AB, and then you have some continuous real valued function which lives on this compact interval. And the range of this function is what we denote by S. So that's the collection of all f of x's. So if you have any x in between A and B, then you go up like this, and then this is the point on the graph. So this is x comma f of x. So its y coordinate is f of x. So you can think of this S sort of that at far away at infinity there is the sun, which is sending out parallel light rays, which are then blocked by this graph of the function. And then this casts a shadow on the y-axis, which is the range of the function. And this is a bounded set, so it has a supremum and an infimum, and if this is the supremum, then the extreme value theorem says that it is attained. So there is some point C in the domain such that f of C is equal to this supremum, and if this is the infimum, then there is some point D in the domain such that f of D is equal to this infimum. And we know that the supremum is the least upper bound of the set. So in particular, it's an upper bound. So this f of C is an upper bound of the set. Of what set? Of the range. So f of C, the upper bound, is bigger than or equal to each member of the set. And the members of the set are these f of x's, where x belongs to AB. So we have that f of C is bigger than or equal to f of x for all x's in AB. In other words, the value that f attains at C is the largest value, and so C is a maximizer of the function. And similarly, f of t, which is this infimum, is the greatest lower bound. In particular, it's a lower bound, and so we have that this lower bound is less than or equal to each member of the set. So f of d is less than or equal to f of x for all x's in AB. In other words, the value at d is the smallest possible, so d is a minimizer of f. So here are a couple of remarks about the extreme value theorem. First of all, if either of the assumption of the continuity of the function or the fact that its domain is a compact interval is dropped, then the conclusion may not hold. And after looking at the proof of the extreme value theorem, we will see some concrete examples which illustrate this. And the second thing is that the theorem doesn't say anything about how many maximizers or minimizers the function has. So it can have more than one. So an extreme example is the constant function, where every point in the domain is both a maximizer or a minimizer. And as another example with finitely many, you can consider the sine function on some big compact interval, for example 0 to 4 pi. So here is 2 pi and here is 4 pi, and then this part is repeated so that we see that there are two maximizers and two minimizers. So the next task is to prove the extreme value theorem, and before we do that, let's prove a lemma which will be useful in the proof. So this lemma says that a subset S of the real numbers is bounded if and only if the set mod S is bounded, where mod S denotes the set which is consisting of all mod x's where x belongs to S. So whatever are the elements of S, you take the absolute value of that and that's put in this set mod S. So S is bounded if and only if mod S is bounded is what we have to prove. So of course there are two implications we have to prove. If mod S is bounded, then we have to show that S is bounded, and vice versa. If S is bounded, then mod S is bounded. So let's begin with the if part. So we assume that mod S is bounded. So in particular, then mod S is bounded above, and that means that it has an upper bound. So there exists a real number u such that for all the elements of mod S, you have that the element is less than or equal to u. But elements of mod S are of the form mod x, where x belongs to S. So we have that for all x's in S, mod x is less than or equal to u. Now this means that x itself is less than or equal to mod x. Of course we know that, and that is less than or equal to u. So x is less than or equal to u. And on the other hand, minus x is also less than or equal to mod x, which is less than or equal to u, which gives that x, if I take this on this side and u on the other side, then we get that x is bigger than or equal to minus u. So we have that for all x's in S, x is less than or equal to u from here, and x is bigger than or equal to minus u from this part. So you have that every element of S is less than or equal to u and bigger than or equal to minus u. So that means that u is an upper bound of S and minus u is a lower bound of S, and so S is bounded. So we have proved that if mod S is bounded, then S is bounded. Now let's prove that if S is bounded, then mod S is bounded. Well, S bounded means what? It has an upper bound and a lower bound. So there exist real numbers u and L such that for all x's in S, x is less than or equal to u and x is bigger than or equal to L. But if x is less than or equal to u, then x is of course also less than or equal to maximum of u and minus L, because this is going to be something bigger than u. Okay. And on the other hand, the reason I introduced this minus L is because you see this inequality rearranged says that minus x is less than or equal to minus L, which is again less than or equal to maximum of u and minus L. So you have got that both x as well as minus x are less than this number. So the mod of x, which is one of the two, is certainly going to be less than or equal to this big number. So for all x's in S, mod x, which we know by the definition is always going to be bigger than or equal to 0, is less than or equal to this number, maximum of u and minus L. And so this mod x has a lower bound and an upper bound. Okay, so for all the elements of mod S, which are of the form mod x for some x in S, you have that element lies between these two numbers. So this is a lower bound for mod S, and maximum of u and minus L is an upper bound. So we have got a lower bound 0 and an upper bound for mod S, and so mod S is bounded. Okay, so this proves this lemma, and this lemma essentially says that the boundedness status of a set is the same as the boundedness status of mod S. Okay. Okay, so now we are ready to prove the extreme value theorem. So let's first recall what the extreme value theorem said. It said that if you have a real valued continuous function living on a compact interval AB, then several things happen. First of all, the range or the image of the function is a bounded subset of the reals, and since it's non-empty, then we know that the supremum of that set and the infimum of that set exist. And most importantly, the extreme value theorem says that these values are attained. Okay, so let's start with the first conclusion, namely that the image or the range of this function is bounded. So let's denote the range or the image by the letter S. So this is the set S, which comprises all the f of x's where x belongs to the domain, which is this compact interval, and we want to show that this set is a bounded subset of the set of real numbers. So we prove this by contradiction. Let's suppose that S is not bounded. Now by the lemma that we just proved, we know that S is bounded if and only if mod S is bounded. Okay, so since we are assuming that S is not bounded, then mod S cannot be bounded either, because if mod S was bounded, then S would be bounded, which we know is not bounded. So mod S is not bounded, but mod S is bounded below. After all, mod S is the collection of the absolute values of things in S, and so this absolute value is always bigger than or equal to 0. So we know that this mod S has a lower bound, namely 0. Now since mod S is not bounded and it has a lower bound, what can go wrong is that it doesn't have an upper bound. So this means that mod S is not bounded above. So no real number can work as an upper bound. Okay. So now we produce a sequence in the following way. Let n be any natural number. Then we know for sure that n is not an upper bound of mod S. That means that there must exist some element in mod S which prevents this n from being an upper bound. Okay. But the elements of mod S are of the form mod f of x, where x belongs to AB. So there must exist some bad xn in AB, such that when I look at mod of f of xn, that is not less than or equal to this n, but is actually bigger than n, preventing this n from being an upper bound of mod S. Okay, so if I take n equal to 1, I get such a x corresponding x1 such that mod f of x1 is bigger than 1. Then I take n equal to 2, and there exists a x2 in AB such that mod of f of x2 is bigger than 2, and so on. So I get a whole sequence x1, x2, x3 and so on, all of which belong to this compact interval such that the mod of f of xn is bigger than n. Now this sequence which we produce in this manner is a bounded sequence. Why? Because each of these xn's belongs to this compact interval. In particular, xn is bigger than or equal to a and less than or equal to b. Right? So this a serves as a lower bound for this set comprising the xn's, and b serves as an upper bound. Okay, so this sequence is then bounded because we had long ago learned this theorem on what it means for a sequence to be bounded. If the set consisting of all the terms of the sequence, if that is a bounded set, then the sequence is bounded. So we know that this sequence is bounded, and then by the Bolzano-Weierstrass theorem, we know that it must have a convergent subsequence. Recall that the Bolzano-Weierstrass theorem says that every bounded sequence has a convergent subsequence. So in particular, this bounded sequence, xn, has some convergent subsequence. Let's call it xnk, where k belongs to n. And since this subsequence is convergent, it has some real limit. Let's call it L. But you see that xnk is also less than or equal to b and bigger than or equal to a for all the k's. So by passing to the limit as k tends to infinity, we then get that the limit should also obey the same inequalities. So you will have that L is bigger than or equal to a and less than or equal to b. Okay, so we have in fact that the limit also belongs to this domain of the function. So you have a sequence, this xnk, the subsequence, which converges to a point L in the domain of the function, and each of these xnk's also belongs to AB. But the function is continuous on the whole interval. In particular, it is continuous at this point L, and so by the characterization of continuity via convergent sequences, you know that since xnk converges to L and each of these belongs to the domain, you have that f of xnk converges to f of L. Now since this sequence fx and k, where k belongs to n, is convergent, it is bounded. Since it's bounded, there exists some bound, so there exists a positive number m such that for each k, mod of fx and k is less than or equal to m. So we have that mod of fx and k is less than or equal to m for all k, but on the other hand, by the way this sequence was constructed, we know that for each index, mod of fxn is bigger than n. So if I think of this index nk, then mod of fxnk is bigger than nk. And since you have this as a subsequence, long ago we had shown this inequality by induction that nk is always bigger, at least as big as k. So you have got that for each natural number k, k is less than or equal to m. That is, the set of natural numbers has an upper bound, which is absurd. It violates the Archimedean property. So we have arrived at a contradiction, and this contradiction shows that our original assumption that this range of the function is not bounded cannot be true, and so the range of the function is bounded. So we have now shown that the set S is bounded, and that was the first conclusion. The second conclusion is that the supremum and the infimum of this set exist. Well, this S, the range of the function, is a collection of real numbers. So this is a subset of R. It is non-empty because, for example, FA and FB both belong to the set. So this is certainly not empty. And we have just shown that S is bounded. So in particular, it's bounded above and bounded below. So by the least upper bound property of the set of real numbers, since you have a non-empty subset of R which is bounded above, the least upper bound of this set exists. In other words, the supremum of this set exists. And by the greatest lower bound property of R, again, since you have a non-empty subset of R which is bounded below, the greatest lower bound of S also exists. In other words, the infimum of S exists. We now have to show that the supremum of S and the infimum of S are attained, so they belong to the range. In other words, there exists some point C in the domain of the function such that f of c is the supremum, and there exists some point D in the domain of the function such that f of D is the infimum. So let's begin with this first part where we show that there exists a point C in the domain of the function in this compact interval such that f of c is the supremum of S. So the way we will produce this C is as the limit of a certain sequence, and to produce this sequence we proceed as follows. So for any natural number n, we look at the number, the supremum of S minus 1 by n. Now that is strictly less than the supremum of S, and this is the least upper bound of S, and now we have a number which is strictly less than that. So this cannot be an upper bound of S. Now since this number is not an upper bound of S, there must be some element of S which prevents this from being an upper bound, and we denote that element by yn. So there exists some element, some bad element of the set yn which prevents this number from being an upper bound. So yn is not less than or equal to this number, but in fact strictly bigger than supremum of S minus 1 by n. On the other hand, yn belongs to S, and so it's less than or equal to each upper bound of S. But this supremum of S is the least upper bound. In particular, it's certainly an upper bound. So we also know that yn is less than or equal to the supremum of S. And by the defining property of yn, we also have that yn is strictly bigger than the supremum of S minus 1 by n. And this happens with each natural number n. So we have got this sequence y1, y2, y3 and so on, such that these inequalities are satisfied by the yn. Now if you look at the sequence whose nth term is supremum of S minus 1 by n, then since this 1 by n converges to 0 as n tends to infinity, it follows that this sequence converges with limit supremum of S. On the other hand, consider the constant sequence, each of whose terms is the supremum of S. So then of course that constant sequence is also convergent with the limit supremum of S. And this sequence yn is in between these two, both of which have the same limit, namely the supremum of S. So by the sandwich theorem, this middle sequence is also convergent with limit supremum of S. Now each of these yns belonged to S, and recall that S was the range of the function, the image of the function, and so for each n, this yn which belongs to the range is actually f of xn for some xn belonging to the domain of the function, which is this compact interval AB, right? So we have that each of these xn's belongs to this compact interval. So in particular, it's bigger than or equal to A and less than or equal to B. So that means that this sequence xn is bounded. Now the Bolzano-Weierstrass theorem says that every bounded sequence has some convergent subsequence. So if we apply that to this bounded sequence xn, it will have some subsequence xnk which is convergent. And let's denote the limit of this subsequence xnk by c. Now we know that for each index n, xn is less than or equal to b, bigger than or equal to a. So if you look at these indices, nks, then you have xnk is bigger than or equal to a and less than or equal to b. So passing to the limit as k tends to infinity, the limits will also obey the same inequalities. So you have that the limit of xnk, which is c, is bigger than or equal to a and less than or equal to b. So in other words, this c belongs to this compact interval. On the other hand, each of these xn's also belong to this compact interval, so each of these xnk also belongs to the domain of the function. So you have a sequence, this xnk, all of which belong to the domain of the function, and they are this sequence is convergent with a limit which also belongs to the domain of the function. And we know that the function is continuous on the whole interval. In particular, it's continuous at c. And by the characterization of continuity via convergent sequences, then we know that f of this kth term, so f of x and k, that new sequence, is convergent with limit f of this limit. Okay, so f of c. So we know that f, x and k converges as k tends to infinity to fc. And what is this f, x and k? That's nothing but y and k. So you have got that this y and k, which is a subsequence of this yn, converges with limit fc. But this sequence was itself convergent with limit the supremum of s. And then a while ago we had learned that whenever you have a convergent sequence, then each of its subsequences is also convergent with the same limit. Okay, and here is a subsequence which we have shown is convergent with limit fc. So this subsequence converges with limit fc, and being a subsequence of this convergent sequence, it converges with limit supremum of s. So by the uniqueness of limits, it must be that this supremum of s is equal to f of c. Okay, and so we have got that this c, which was the limit of this convergent subsequence x and k, is a number such that f of c is equal to the supremum of s. So we have got our c in the domain such that f of c is the supremum of s. And note that since this fc belongs to the range of the function, we have that this fc, which is the supremum of s, belongs to s, so this supremum is actually a maximum. So the way we produced this c was we first looked at the supremum of s minus 1 by n, and since that's not an upper bound, we got this sequence yn. We proved that this yn is convergent, and this yn is f of xn for some xn. We got a bounded sequence by Bolzano-Weierstrass that has a convergent subsequence. We use the continuity to show that then f of this subsequence, which is this y and k, is also convergent with limit fc. But y and k converges with fc, and being a subsequence of this, it converges with limit supremum of s, and so we got that fc is equal to the supremum of s. So it remains to show that the infimum of s is also attained. In other words, there exists a point d in the domain of the function in this compact interval such that f of d is the infimum of s. And we can give a similar proof of this as we did to show that the supremum of s is attained, but we give a different argument which is shorter, and that's based on looking at the function minus f. So our original function is a continuous function which is real valued and lives on this compact interval ab, and suppose we pointwise multiply this function by the real number minus 1. Then we get this new function which we denote by minus f. It's real valued and has the same domain, this compact interval. And since the original function is continuous, from the algebra of continuous functions, we know that this new function is also continuous. Now, by what we have shown so far, if we apply all those results to this new function minus f, we know that the range of this minus f is bounded, and the supremum of its range is attained. So by part 3, which we have just proved, applied to this new function minus f, we know that there exists a point d in its domain such that minus f at d is the supremum of its range. Okay, and its range is all the minus f acting on x's where x belongs to AB. Now by definition, minus f at d is nothing but minus fd, and minus f at x is nothing but minus f of x. Now we call the set S to be the set comprising all the f of x's such that x belongs to AB, the range of the function f. And minus s is then the collection of all the minuses of the elements from S. Okay, so minus s will then be minus fx where x belongs to AB. Now long ago we had this exercise where we derived the greatest lower bound property of R using the least upper bound property of R, and along the way we had shown that if S is a non-empty subset of R which is bounded below, then the infimum of S exists, and in fact the infimum of S is minus the supremum of minus S. In other words, minus the infimum of S is the supremum of minus S. Now this S that we have, the range of f, that we know is a bounded set and non-empty, so the infimum of S does exist, and by that exercise then we know that the infimum of f of x where x belongs to AB is nothing but minus the supremum minus f of x where x belongs to AB. So from that we get that this supremum minus f of x where x belongs to AB is nothing but minus the infimum of f of x where x belongs to AB. Okay, and this is nothing but minus the infimum of S. So we have got that minus fd is minus the infimum of S. The minus cancels and we hence get that the infimum of S is f of d for some d in AB. So we have got that the infimum of S is also attained, and since this fd itself belongs to the range of the function f, this means that the infimum of S belongs to the range of the function, and so this infimum is actually a minimum. Okay, so this completes the proof of the extreme value theorem. And let's also remark once again that since this supremum of S is an upper bound of the range of the function, we know that the supremum of S is of course bigger than or equal to each member of the range. So for all x's in AB, f of x is less than or equal to the supremum of S, and since this is attained, this is FC. So we have got that for all x's in AB, f of x is less than or equal to FC. In other words, C is a maximizer of f. And similarly, if the infimum of S is fd, then this is the greatest lower bound of the range. So in particular, it's a lower bound. So that's less than or equal to all the elements of the range. So for all x's in AB, f of x is bigger than or equal to fd. And so d is the smallest value possible of the function, and so d is a minimizer of f. So here is a first example, and in this example we'll show that if f is a real valued continuous function on a compact interval AB, which is pointwise positive, and I'll explain what that means, then in fact the function is bounded away from 0, and I'll also explain what that means. So here is the precise statement. So suppose that f is a real valued continuous function living on a compact interval AB, which is pointwise positive, by which we mean that no matter which x you take in the domain, f of x is strictly positive. Okay, so at each x you have a positive number. Then in fact f is bounded away from 0. What does that mean? That means that there exists a positive delta such that for all x's in AB, f of x is actually bigger than this delta, and which is a positive number. So sort of f of x, the values of f of x are uniformly bounded away from 0. There is some gap here, okay, some positive distance delta. So you consider the horizontal line which is at this height delta, and then the graph of the function lies above this line. Okay, so that's what this inequality means. So how do we prove this? Well, by the extreme value theorem, we know that this f has a minimizer. Let's call the minimizer d. So that's some point in the domain such that f of x is always bigger than or equal to f of d. Okay. Now, since the function is pointwise positive, we know that at each point in the domain, the value of the function at that point is positive. So in particular, since d is a point in the domain, the value of the function at d, let's call it delta, is a positive number. But now for all x's in AB, since d was a minimizer, we know that f of x is bigger than or equal to fd, but fd is what I called delta to be. So you have that for all x's in AB, f of x is bigger than or equal to this delta, which is a positive number. So there is this uniform gap, which is actually the value of that function at this minimizer. So we'll now give some examples which show the role of the two conditions, the compactness of the domain of the function and the continuity of the function, which are the hypotheses in the extreme value theorem. So here are some examples of functions f which live on the interval I and are real valued, and we will record whether the domain of the function, this interval I, whether it's a compact interval, whether the function is continuous, and if S denotes the range of the function, does the supremum of S exist, does the infimum of S exist, and if they do, then are they attained? So do they again belong to the range of the function, the supremum and the infimum? Okay, so our first example is when the interval is this open interval 0, 1. It's not a compact interval, and the function is the reciprocal function. Now, since the reciprocal function we had shown is continuous on the whole of the positive real line, so on the open interval 0, infinity, in particular its restriction to this open interval is also continuous. Okay, and the graph of the function looks like this. It always lies above 1. And in fact, the range of the function is this open interval 1 infinity. And let's see what are the answers to these questions. Is the domain of the function a compact interval? The answer is no. Is the function continuous? Yes. Does the supremum of S exist? No, it does not, because the set is not bounded above. Does the infimum of the range exist? Yes, it does. The infimum is equal to 1. But the infimum is not attained because there is no real number in this open interval whose reciprocal is equal to 1. So the infimum of S is not attained. So the supremum does not exist, so the question of its attainment does not arise. The infimum of the set exists, but it is not attained. Okay, and this is not really a surprise because we are not in the context of the extreme value theorem. The extreme value theorem says that only when the function is continuous and the domain of the function is a compact interval are all these things supposed to exist and be attained. Okay, so but the domain here is not a compact interval. Okay, so things can go wrong if the domain is not a compact interval. Now over here the supremum didn't exist, but it can happen that both the supremum and infimum exist but they are not attained. Again, perhaps because the domain is not a compact interval. So here is an example of that. So again, let's take this open interval as the domain, and the function now is the identity function. The function is again continuous. The domain is not a compact interval, and the range of the function then we see is this open interval 0, 1. So the supremum of this interval does exist. It is equal to 1. The infimum also exists. It is equal to 0, but none of them are attained. Okay, and so although the supremum and the infimum exist, they are not attained. And again, this is not really a surprise because we are not in the situation of the extreme value theorem because the domain is not a compact interval. Now here is a third example where despite the fact that the supremum and infimum again exist, they may not be attained, and now it's not the compactness which goes wrong, but actually the function is not continuous. So rather than give an explicit formula for the function, we just sort of graphically illustrate what the function is. So first of all, the function lives on this compact interval 0 to 1. Okay, and the function is defined in two parts. For values of x's which are strictly less than half, it increases linearly all the way up till 1. But at half, the value is not over here, but it jumps to 0. And then for values of x which are strictly bigger than half and less than or equal to 1, it again decreases linearly from over here. So clearly the function is not continuous at half because there is this jump. What is the range of the function? Well, 0 is attained and otherwise the values are in between 0 and 1. So the range of the function is this interval where one endpoint is 0, which is included, and the other endpoint is 1, which is not included. Okay, so is the domain a compact interval? The answer is yes. Is the function continuous? No, because the function is not continuous at half. Does the supremum of this set exist, of the range of the function exist? The answer is yes. The supremum is equal to 1. Does the infimum of this set exist? The answer is yes, it exists and it is equal to 0. Is the infimum attained? Yes, it is attained because f of half is equal to 0. But is the supremum attained? The answer is no, because there is no x such that f of x is equal to 1. Okay, so the supremum and infimum existed. The supremum was not attained, but the infimum was attained. Okay, and as our final example, we show that, well, these conditions are not necessary. So even if both are violated, it can happen that all the conclusions of the extreme value theorem still hold. Okay, so here is such an example. So suppose my domain is this interval, open interval 0, 1, which is not a compact interval because the endpoints are excluded, and the function is not continuous either. So the function is defined like this. It is mostly 1 except at half the value jumps from 1 to 0. So the function is not continuous on the whole interval because it is discontinuous or not continuous at half. Domain is not a compact interval, the function is not continuous, but let's look at what the range is. The range comprises just 2 points, 0 and 1. So the supremum of course exists, it is equal to 1. The infimum also exists, it is equal to 0. And these values are attained because if I take, for example, f of 1 by 4, that is equal to 1, and f of half is equal to 0. So you see that the supremum exists, the infimum exists, the supremum is attained and the infimum is attained, but neither the domain was compact nor the function was continuous. The extreme value theorem has theoretical use. It says that if you have a real valued continuous function on a compact interval, then it has a maximizer and a minimizer. But let's see an example which shows the practical use also in optimization. So in calculus, you might have met the following theorem, which says that if you have a differentiable function on an open interval, and if a maximizer exists, then the derivative of the function at that point must be 0. Sort of pictorially, if you have a function living on this open interval which is differentiable, and if there is a maximizer, then at that point the tangent line to the graph of the function at that point should be horizontal. So the derivative at that point should be 0. But this theorem is useful only if you know that there exists a maximizer. And it is in this part, the existence of the maximizer, that the extreme value theorem can be useful. So let's see a concrete example. Suppose that you have a real valued function on this compact interval which is given by f of x is equal to cos x plus x by 2, where x is bigger than or equal to 0 and less than or equal to pi by 2. And the optimization problem we are considering is that of maximizing f on this interval. Now by the extreme value theorem, we know that a maximizer for f exists in this compact interval 0 to pi by 2. But let's show that neither 0 nor pi by 2 is a maximizer. So the maximizer has to lie in the open interval 0 to pi by 2, and then we can use this calculus theorem. Okay, so first of all, f of 0 is equal to cos 0 plus 0 by 2. Cos 0 is equal to 1, so you get 1 plus 0, which is equal to 1. On the other hand, f at pi by 2 is cos pi by 2 plus pi by 2 by 2. Cos pi by 2 is 0, so you get pi by 4. Now since pi is less than 4, this is strictly less than 1. So in fact the value at pi by 2 is even smaller than the value at 0. So certainly pi by 2 cannot be a maximizer. We also show that 0 is not a maximizer because the value at some point in between 0 and pi by 2 can be bigger. So for example, the value of the function at pi by 3 is cos pi by 3 plus pi by 3 by 2. And what is cos pi by 3? Pi by 3 radians is actually 180 by 3 degrees, and that is 60 degrees. And so if you look at an equilateral triangle and drop the altitude, then this angle is 60 degrees and this is 30 degrees. And then the altitude, if the side length is 2, half of the side length is 1, the altitude is then root 3 by Pythagoras theorem. It will be square root of 4 minus 1, which is root 3. And so cos of 60 degrees will be a half. So this f of pi by 3 is half plus pi by 6. Now pi is bigger than 3, so this is bigger than half plus 3 by 6. 3 by 6 is half, half plus half is 1. So the value at pi by 3 is bigger than 1. It's bigger than this endpoint value. Okay, so the endpoints cannot be a maximizer, and extreme value theorem has told us already that there exists a maximizer. So this maximizer has to belong in the open interval. Okay, and if it's a maximizer for the function on this compact interval, it's certainly a maximizer on the open interval as well. So now we are in the situation where we know that there exists a maximizer, and the maximizer in fact belongs to this open interval 0 to pi by 2, and then we know that then the derivative has to vanish at that point. So let's see what the derivative is and where it vanishes. The derivative, this is a differentiable function, and the derivative is minus sine x plus half, and that is 0 at only one point in this interval, and that point is when x is equal to pi by 6. Okay, because you get sine x is equal to a half, and the only x in 0 to pi by 2 which has that sine of x is equal to half is when x is equal to pi by 6. Okay, basically 30 degrees. So that is then the maximizer of this function. Use of the extreme value theorem was to give the existence of the maximizer, with which then we could use this calculus theorem to determine the maximizer. So this actually finishes chapter 3. So this concludes the analysis part of this course. And in this analysis part, we had 3 chapters. We began with a discussion of the real numbers and the least upper bound property. Then chapter 2 was on sequences and their convergence, and chapter 3 was on continuity. So what comes next? First of all, let me talk about this course. So for students of MA 103, the first part of length term will again be given by me, in which we will cover chapters 4 and 5 of my lecture notes. In chapter 4, we will actually construct the real numbers starting from an axiomatic development of the natural numbers. So we'll start with the natural numbers, and then we will construct the integers, the rational numbers, and finally the real numbers. And along the way, we'll prove all the properties that we have been taking for granted for these number systems. For example, the trichotomy law for order. Okay, and once we do this, then chapter 5 will focus on the set of integers together with its 2 arithmetic operations of addition and multiplication, and we will talk about things such as divisibility, the prime numbers, and prove a very important result in all of mathematics called the fundamental theorem of arithmetic, which says that every number can be decomposed and written essentially in a unique way as a product of primes. So just like all the matter that we see around us is made of atoms, in the same way these prime numbers are really the atoms of the numbers, and we will state and prove this fundamental theorem of arithmetic. So I'll also say something about what lies beyond the horizon with respect to the analysis part. So what we have learned are the foundations of analysis, but then beyond that one would learn about things like differentiation and integration and the fundamental theorem of calculus and so on. So in this regard, there are these 2 courses, MA 203 and MA 212, and some of you might be taking this. So in MA 203 on real analysis, you will learn about calculus in the setting of RD, so sort of multivariable calculus, and more generally in the context of finite dimensional vector spaces. So you will soon learn, for those of you who are following MA 103, what a vector space is and what it means for it to be finite dimensional. And real analysis is all about doing calculus in such spaces. And in this companion course, which is more of a methods course called Further Mathematical Methods, there are 2 parts. One is on calculus and the other is on linear algebra. And in the calculus part, you will learn about differentiation and integration and the fundamental theorem of calculus, and also in the multivariable context of several real variables. And analysis, of course, is fundamental in all of mathematics, so one can also do calculus in more exotic spaces, for example in the complex numbers, and then it's a subject called complex analysis, which is quite different from real analysis. It turns out because of the special geometric meaning associated with complex multiplication. It turns out that complex analysis is not just about doing calculus in C, but is actually more specialized. It's the study of complex differentiable functions. And the course MA 317, third year undergraduate level, treats this subject over here at LSE. And then at the graduate level, there is also a course called Functional Analysis, in which there is an interplay of linear algebra and calculus. Here one does calculus in the setting of vector spaces, which are spaces of functions. Okay, vector spaces of functions, and these are called function spaces. And more abstractly, one can also look at infinite dimensional vector spaces, and that's the subject of functional analysis. So analysis is quite fundamental in all of mathematics. Okay, so that's what lies beyond the horizon, and that's the end of the lectures for the Michaelmas term. Some of you, those following MA 103, I'll again meet in the beginning of the Lent term, the first 5 weeks. We'll cover chapters 4 and 5 of my lecture notes. Okay, I wish you a pleasant break, and I'll see some of you in the Lent term.